Hi everyone. I'm recording our lesson today. We should have discussed this worksheet slope and intercept and this other worksheet SSR, SSE and SST today, but because classes were suspended, we were not able to do that. So since we have limited time, I decided to record this and post this to our Canvas, and I hope you'll follow along. And I hope you're going to do this also in your worksheet. So let me invite your attention to this worksheet. The title is Slope and Intercept. Okay, we have been talking about regression, and we said that the purpose of determining or coming up with a regression line between two variables, one is the dependent variable, and the other one is the independent variable, is so that we are able to best describe in this case, the dependent variable. We'd like to understand more the dependent variable. So it's not only for descriptive purposes. We do regression also for predictive purposes. We'd like to establish a relationship between the two variables so that we can predict your dependent variable, in this case, sales, if we're given a particular value of your X, which is your weekly ads in our case. Okay, so we said that the regression line can be determined by the equation. So our equation is y. In this case, y is our sales. It's equal to a certain value. This is your intercept b null plus b1 multiplied by your independent variable x, which is your ads. Okay, so in order to establish the relationship between your dependent variable and independent variable, so this is multiplication, we need to compute for the b null, which is your intercept, and your b1, which is your slope. Okay, so if we're able to compute for this, then we're able to generate a quantitative relationship between your dependent variable sales and your independent variable ads. The question is, how do we compute for beta null, B null, and B1? Okay, so we use a particular formula. The formula to compute for your B1 is given by this one. Okay, so B1, which is your slope, is equal to the cross product of the deviation of your X values with the mean and Y values with the mean of Y. And then we divide it by n minus 1. If you recall, guys, this is your covariance of X and Y, right? This is the covariance of X and Y, which is also written as SXY, okay? So we have for the numerator, the covariance of X and Y. Now, for the denominator, if you take a look at this is a summation of the squared deviation from the mean of X. So we square it and then divide it by negative n minus 1 to indicate that this is a sample. Okay. However, this is, do you know what this is? From your stat, that is your that's your variance of X. Okay, that's a variance of X. So therefore, guys, B1, the slope, can be computed by SXY, the covariance between X and Y, and then the variance of X. All right? So this is how we can compute for your B1, the slope. Last meeting, we actually solved for this using the slope function in Excel. Okay? All right. Now, this can also be expressed in another way. If you recall, what is the relationship between R? Okay, so we want to express B1 in terms of your R. Okay, your R, which is your Rxy, your correlation. Because here we're expressing B1 in terms of the covariance. Okay, so by the way, we just okay, yeah, the whole numerator term is your covariance. The whole denominator term is your variance of X. So don't be surprised if sometimes you'll see this written as the cross product of the deviations between your Y and X divided by just the deviation from X squared. Okay, this is your, by the way, this is your B1, okay? So we can solve for B1 using these formulas. Now we can also express B1, so these are the same, in terms of R correlation, okay? So we know that R, recall R, guys, R is equal to, what's the formula for R? R is related to your covariance by dividing it by its standardized values, right? So this was a formula we learned last time. Okay, so from this, we know that your covariance between X and Y is your correlation multiplied by standard deviation of X and standard deviation of Y, all right? So last time we were able to establish this relationship that the covariance of X and Y between two variables is related to their correlation, okay, by just multiplying it by its the standard deviations of your variables. Okay, so if we substitute xy, if we substitute this with this one, we will now be getting B1 is equal to your covariance is equal to your R multiplied by standard deviation of X, standard deviation of Y. Okay, so this is this one, and then follow this divided by the variance of X. Okay, which now reduces into B1. So B1 is now equal to the correlation between X and Y divide times what? Times the standard deviation of Y divided by the standard deviation of X. All right. So in this portion, guys, we see that there are different ways to compute for your B1. So it can be expressed in this way, summation of X minus X bar times Y minus Y bar over summation of X minus X bar squared. Okay, either this one or also this one, they're the same. Or we can express it in terms of R, the correlation, which is this one. Okay, so we have three ways to express our slope B1. Okay, then once we have computed for B1, once we have computed for the slope, then we can compute for the intercept beta null, and it's equal to this formula. We're going to make use of the slope that we were able to compute first. Where's my... this one. So we get the average of y minus the slope that we were able to compute using this formula times x bar. Okay, to give us this equation, y hat, hat means that this is the predicted value or forecasted value. Predicted value is equal to your intercept plus your slope times your x. So in this case, we're using x to predict the values of y. We're using the independent variable to predict our dependent variable. All right. Having said those, guys, let's now, so what do we need? In order to compute for your B1, we need the covariance or the cross product, the sum of the cross products of their deviations. Okay, so let's compute for that x minus x bar times y minus y bar. We're going to do that here. Okay, and then we're going to divide it by x minus x bar squared. So these columns here will be used to compute for your B1. And then let's validate that using the slope function of XL. So first, let's solve the numerator. It's x minus x bar times y minus y bar. We actually have done this in the past. So let's do this. Let's count. And then we need n minus 1. So let's count minus 1, 189. This one we have actually solved this before. So that I'm going through this very quickly. Average of x. Let me just copy this. And then let me just change this to C. Average of y. All right. Okay, so let's solve for slope using this formula. And let's try to validate if indeed it agrees with the slope function of XL. All right, first we compute for the deviation of x from the mean, deviation of y from the mean, and then we're going to get their cross products. Okay, so this is x minus x bar, and then we fix this. We're just going to fix the row because we're going to copy this down. Okay, and we know, guys, that the sum of this should be equal to 0. Okay, we know that the sum of the deviations from the mean will always be equal to 0. The same thing for your y. This minus are the average of y. Then we'll fix that. Control Enter. And then let's copy this down and copy the total. Okay, as expected, it should be 0. So we have x minus x bar times y minus y bar, and then y minus y bar. Then we get the cross product. So we're just multiplying x minus x bar and y minus y bar. All right. And what we do now is we also get the sum of this. All right, so this will be our numerator. Okay. Then when we divide this by x minus x bar squared, we can just cancel out n minus 1. So whether we use this, we consider this as a sample or as a population guide, it does not matter. Because if this was n, this will also be n. So we can just cancel those. All right, so let's now get the deviation of x, which is just x minus x bar. Okay, so we just squared this, right? X minus x bar, and then square it. Right, so let me just decrease the decimal place. We actually don't need so many decimal places. And then we add this. Okay, so that takes care of the sum of x minus x bar squared. So when we compute for B1, it will be the summation of the cross product of x minus x bar times y minus y bar, which is this one, then divided by x minus x bar squared, which is this one. Okay, we said that the divisor n minus 1 will be irrelevant for this because it will just cancel out. Okay, so B1, the slope will be equal to, it will be equal to x minus x bar summation divided by x minus x bar squared deviation, sum of that. Okay, so it's 8.2415, right? 8.2415. And let's validate this. Let's use the slope function that we used last time. So the slope function of XL returns the slope of the linear regression line through the given data points. So slope, now we need to first highlight the y's, the independent variable. So this one, and the x, this one. All right, so it's the same. So we confirm, guys, that indeed to compute for the slope, yes, we can use this formula. Okay, we can use this formula, which is just the same also as this formula. Okay, that's a covariance divided by the variance, or we can express the slope in terms of correlation times the standard deviation of y divided by the standard deviation of x. Okay, so okay, if you want, okay, we can validate this. So B1 is equal to correlation times standard deviation of y over standard deviation of x. So let's do that. So this is equal to, it's a correlation. Remember, we used this last time. Correlation between x and y. Doesn't matter if you highlight x first and then y. So this will be your correlation. Okay. If you recall, this is, so let me just write R times S y divided by S x. Okay, so this is your R, this is your correlation. Then we have to multiply it by the standard deviation of your y. This is your y, right? It's a standard deviation of your y divided by the standard deviation. So we're using it as a sample of x, which is your odds. There. Right? So this is the correlation multiplied by the standard deviation of y divided by the standard deviation of x, and you get the same answer. So exactly the same answer. Okay? So we have learned to express the B1, the intercept, the slope, I mean, in different formulas. You get the same, guys. It's the same answer. So this is just the slope function of XL. All right. Now to get the intercept, we use this formula. Beta null, the intercept is equal to average of y minus the slope times the average of x. So we can do that. So this is equal to the average of y, okay, minus your slope B1 times the average of x. Okay. So let me just remove the dollar sign. All right, so this is your your intercept. Okay. All right, there's another formula here for slope. Okay, I think we already did this, so we can just link this here. Okay, so this is correlation times Sx divided by Sxy, or you can just get the automatically the slope of the regression line. And then this one, let's validate that using the intercept function. Intercept known y's, comma, known x's. Remember that your y is your weekly sales, your dependent variable, and your x, which is your ads, is your independent variable. Okay, so we get the same. All right, so now our equation is y sales is equal to, our intercept is 36,857, and plus 8.24155 multiplied by your x ads. Okay, so this is now our regression equation. And remember, guys, that we come up with the regression equation to better understand our dependent variable, how it moves in relation to your independent variable x ads. Okay, and we say that your sales is related to your ads by 8.24. The marginal effect of ads on sales is 8.24. So by way of review, guys, what do we mean by 8.24? It means that for every $1 of ads, there's a corresponding $8.24 of sales increase. The relationship, as established by the slope, is positive. Okay, it's positive. So which means that if ads increases, then sales will increase. Okay, what about 36,857, the intercept? What does that mean? The intercept, guys, is the value of your sales when your independent variable x is equal to 0. Okay, now care should be taken in interpreting this. Okay, because when we get the minimum value of x, okay, the minimum value of x, let's get the minimum value of x. And the minimum value of y, sorry, maximum value of x. All right, please take note that we are using x, variable x, which is your weekly ads, as a predictor of y, of sales. And x ranges from a minimum of 14.5 thousand to 64.7 thousand. And we call that your relevant range, right? We say that the relevant range of x varies from 14 to 64,000. So any prediction that we are going to do to try to predict your sales based on x should be based on values of x between this minimum and maximum. You can, of course, forecast your y beyond these values, but the value should not be very far from the minimum and the maximum. Now, to say that your sales is 36,857, which is the intercept, implies that your ads is equal to 0. So ads is equal to 0 fall way outside your relevant range. So technically, we cannot actually give a practical meaning or practical implication for the intercept, which is 36,857. However, guys, nevertheless, we still use 36,857 as part of the model in predicting your X, your sales. Okay, so I hope that's clear. As here, guys, we have an equation. We cannot just use any X in the equation. Okay, it's best to use values to forecast your Y, values between X, between the minimum and the maximum. If, for example, we would like to forecast, okay, let's say For example, we're given the X value of 40,000. Can we use this equation to forecast your sales? Yes. 40,000 is within the relevant range. And what we do, we can just substitute 40,000 here, and we'll be able to get your forecasted sales. Right, so let's do that. It's equal to, so the intercept first, let's use the formula. Okay, let's not type the values because this is approximate only. And then plus, you have the slope of 8.24, and then times your X value is 40,000. Okay, so that's your forecast value. Okay, so this is our forecast value. If ads is 40,000, then our prediction is that sales will be 366,518 based on our regression formula. So that's one use of regression. We use it to predict values of your Y, your dependent variable, given a particular value of your independent variable. So how did we forecast? We used the equation, this one. We can actually use also other functions of Excel. So it's possible, guys, it's possible, class, not to compute for your intercept and the slope and still be able to forecast. So how do you do that? Well, we use the forecast function. Okay, so forecast. So we have different forecast functions here. Forecast, this is, I think this is exponential. Okay, and then we use either linear, that linear, or the old function, the forecast, the one with the yellow triangle. It means it belongs to the old Excel versions. So let's use this. We can use this, or you can use the forecast that linear. It doesn't matter. You'll get the same answer. So forecast that linear, we're asked what is the value of your independent variable. So it's 40,000. Then comma, what are our known Y's? Our known Y's are your weekly sales, and our known X are your weekly ads. Okay, so this one, so we get the same value. All right. Or another function we can use is Excel also has the trend function. So trend returns the numbers in a linear trend matching data points using the least squares method. Okay, so we know, guys, that the method used in linear regression is the method of least squares. So trend, known Y's, these are our known Y's, comma, known X's. Oops, what happened? Okay, known Y's, comma, known X's. Okay, and then here you have new X. So what's our new X? Our new X is 40,000. Oops, what happened? Should put a comma here, comma, new X 40,000. And then one more. So where's the syntax here? You have here the last constant. Okay, constant. So what will that give us? Comma. Okay, so we either choose false or true. So false, we choose false if we want to set the intercept to be equal to 1. Okay, if we want the intercept to be equal to 1, then we use false. Otherwise, if we want the intercept to be calculated normally, then we choose we choose true or 1. Okay, so we type true, true, or 1. Okay, and we get the same answer. 366,518.99. All right. Okay, so again, what's the interpretation of your slope? What is the correct interpretation of the slope? This 8.24. We already discussed this, and we said that for every $1 increase in ad expense, okay, weekly sales will increase by $8.24. What is the correct interpretation of the y-intercept? Okay, we said that it's the value of your sales when x is equal to 0. So when x is equal to 0, the equation predicts that the weekly sales will be 36,587. Now again, word of caution, 0, the value of x, when x is equal to 0, is way outside our relevant range or experimental region. Okay? And it will give us an unreliable result because it's way outside the value of your predictor, which is x, is way outside your relevant range. However, we can still make use of your intercept, the 36857, for predictive purposes. Okay? So in this worksheet, we were able to show that we can use different formulas to compute for your B1. As by way of summary, B1, which is the slope, can be computed using this formula. So this is your covariance of between x and y, and this is the variance of x. Okay. So I think, sorry for this. So this should be divided by the variance of x. Okay. And that can be expressed in this form. Okay. And that was expressed by eliminating n minus 1 by canceling that out. Or we said that the slope can be also expressed as, okay, this is just another way to write it. It can be expressed in terms of your correlation. So B1 is equal to your correlation between x and y and the standard deviation of y divided by the standard deviation of x. Okay, then once we have computed for your B1, then we can now compute for our B null, which is equal to y bar, this is the average of y, minus, using B1, using the slope that we were able to compute first, and then multiply the slope by your x bar. Okay, whatever formula, guys, you use, it will yield the same answer. Okay, and then we recall, guys, that the method used in determining your regression line is your OLS, ordinary least squares, or the method of least squares. And the squares, they refer to the square of the error terms, the deviation. Okay, how far your data points are away from your regression line. And we said that it's called least squares, ordinary least squares, because you try to find a line where the squares of the error terms are at a minimum, least, L-E-A-S-T. Okay, let's move on to the next worksheet, Ssr Sse Sst. So this is very important as far as regression is concerned. Okay, there are many measures like the coefficient of determination, which is based on this concept. So let me first introduce these terms, SST. So we have three terms here, SST, SSR, and SSE. SS here refers to sum of the squares. Okay, sum of the squares. So they only differ in terms of the last letter. This T is total. Okay, so total sum of the squares or sum of the squares total. R here refers to regression, so that sum of the squares due to regression, and E here, sum of the squares of the error terms. Okay, All right. So let's take a look at the formula first. Okay, and then we try to understand what this is and what we're trying to do here. So sum of the squares of the total is just the summation of, these are your y values minus average of y. Okay, y values, actual y values minus the average. And then of course we square that. Recall guys that if we don't square that and we just sum that up, it will give us 0. The answer will be 0. This one, on the other hand, regression, is based on, remember this guys, this is your y hat, is your predicted value. So that's the value of your sales of y when we use the slope and the intercept of the model, and then we use the actual value of your x. Okay, so that's your y sub I. And then we also subtract it from the mean and then square it. Last one here is the sum of the squares of your errors. Okay, so here you have your actual value minus the predicted value. So this is the difference between the actual value and the predicted value squared. Okay, so before we go to this table, let me first explain or illustrate what this SST, SSR, and SSE means. Okay, so let me first increase this. All right. So here we have the scatter plot. We did this before. We have the scatter plot of our model. This line, guys, is your, this is your, what's this? If I extend this here, that's around 300,000. So what's this, guys? This is your y bar, okay? This is your average y. Okay, we actually did that in the previous worksheet. Our y bar is 370,059. Okay, 370,059. This is 370,059. All right. So let's understand what SST, SSR, and SSE means. Okay. So for SST, that's total sum of the squares of the total. What we're trying to do here is that we're not going to use X as a predictor. So for SST, we're just going to use Y values. Okay, which means that we're not going to use X or ads to try to predict sales. Use Y values only. Therefore, if we're going to use the values of Y to predict Y, the best benchmark, the best predictor will be Y bar. Okay, guys? So if we're not going to use X or ads to try to predict Y, then what will be the best, let's say, predictor for Y? Then it will just be the average. It doesn't matter what your ads is. So for example, you're asked, what do you think will be our sales for next week? If you're trying to predict sales. Well, what will be your basis? Just get the average. So we'll say that, well, our prediction is that the sales will be 370. What's your basis for that? The average. Okay. All right. So that's the average, guys. So it's this line. Okay. Now each point here pertains to the actual data point. For example, this one, this point is there. It's okay, sorry. Let me point to that again. Okay, that's 37,237. That's your X. That's your weekly ads, and 453,649. But remember, for SST, we're not we don't care about X. We don't care about your weekly ads. What we're just interested in is the sales itself. Okay, so what we're going to do is we're going to compare all the Y's here, all your actual Y, actual sales, with the average. So let me show that. So this is 370,000, right? So this is your Y bar is equal to 370. What's the exact figure? 370,059. 370,059. 059. Okay? So that will be our basis. So what we're going to do now is we're going to compare each of these elements, each of the Y here, with your mean. Sorry if it's not straight. Okay? There. So each of these guys, we're going to get the difference between the mean and your actual Y. Okay? For those under the mean, it's this one. And this one. Okay? So again, we're looking at SST. How do we compute for sum of the squares of the total? We compare the Y values of each of the points from the average. That's why the formula, guys, is the actual point minus the average. All right? Hope it makes sense to you. So we're going to drop these lines. So these are the deviations. So each of this point, each of this point, guys, deviates from the Y bar by this amount. So that's what we mean by Y minus Y bar, the average. And then we will be squaring it. So let's do it here. Okay, so let's start with this one. It's equal to. So, okay, let me just get the average first. Again, we have done this last time. Okay, and then count minus 1. Then X bar. Then Y bar. Okay. We also have we also have computed for the slope. So let's compute for this slope, which is what we did last time. The slope, known Y's, comma, known X's. Known Y's, known X. And then the intercept is equal to intercept. Again, known Y's, comma, known X's. Okay. Here we'd like to compute for the SST, SSR, and SSE. So let's first start with your SST. Okay, we said that SST is based on Y minus Y bar squared, this one. So we get the actual value of your Y, your sales, subtract it from your average Y bar, and then we're going to fix this. Okay, and then we square it. Control Enter. All right. Okay, take note that all of these are positive already. They're positive because we square the deviations. And then if we add this out, equal to. Okay, so your SST is 3, this is trillion. Yeah, this is million, billion, trillion. 3.2269 trillion. All right. Okay. So that explains, guys, our SST. Sum of the squares of our total is simply the deviation of each y from the mean y bar squared and then add. That's why it's sum. We're summing up, summing the squares. So it's squared, right? Sum of the squares of the total. And the total is based on the difference between your actual y value, okay? Actual y, this is the actual y, minus the average. Okay, so this is y minus y average. So that's a distance. All right. Now we go next to SSR. SSR is the sum of the squares of your regression. Okay. Now, I said a while ago that for SST, we did not use the X values in order to predict Y. We just use the average. That's it. We're not going to use the independent variable adds. Now, to compute for SSR, which is regression, we will have to make use of the regression line, right? So instead of using just the mean, we use a regression line, and it turns out that that regression line is this dotted line here. This is our regression line, which is equal to, as you know, this is already, as you know this, we have already determined this, that's 8.2415x plus 36857. We have this intercept, and we have this slope. So if we make use of this slope and your intercept based on your regression line, then we can have a predicted value of your y. So predicted value of your y is based on this slope and this intercept. And we said that in ordinary least squares, this is a unique value of B1 and B null. There can be only one value of your slope and your intercept. Okay, so let's do that. Let's compute for the predicted value. If you, let me go back here, guys. It's actually, we can use the forecast or the trend function. Okay, we can make use of that, or we can just make use of the slope and the intercept. Either way, we get the same value. All right, so let's just use the slope and the intercept we have computed for. Okay, so our predicted value will be equal to, we just increase the size. Our predicted value will be equal to, let's use the intercept first. This is your intercept. Okay, and then we'd like to fix that. Fix the row because we're going to copy down, which means that the column is not changing. No need to fix $B. No need to fix the column. Okay, and then plus the slope is, this is the slope, 8.24. Okay, and then we fix again your row so that it will not go out of your row. And then we multiply that by the actual X value. Okay, so take note of the formula. Okay, just to show you guys, our prediction line is equal to 8.24 times your X plus 36857. All right. Before I don't need to fix this because we need the values to go down. Control Enter. Okay. All right. So if we sum this up, okay. So these are just the predicted values. So once we know the predicted values, we can now, okay, going back here, your SSR will be the difference between, take a look at this, guys. It's a difference between okay, just to show you, you might not be able to see this. Okay, it's your y hat, which is your predicted value, minus your mean. Okay, so this is your y bar minus your predicted hat. Okay, so what's the concept behind that? The concept behind that is, okay, so this is now our model, right? We used y bar, and then we improved it by this regression line. Okay, so what's the difference between just using your just using your average from your regression line? Okay, so for example, okay, so this is your regression line, this is your average. All right, so the difference between your average, which is our base benchmark, which is our base estimate, and your regression line, means that there was an improvement in your model. So from just using the average to your regression line, okay, the amount by which we were able to improve our model is by getting the difference between the mean and the regression line. The regression line is where you'll have your predicted values. Okay, so your predicted values are all on the regression line. All right? So the difference between them, and then we square the difference, it will give us our SSR, sum of the squares of your regression. So this was how we improved our model, because initially we just used the average, so that's y bar. And then we use the predicted value using the regression line, that's your y hat. So the improvement, okay, can be ascertained, can be computed by getting the difference between your y hat and then your y bar. All right. So let's compute for that. So it is this, guys. Your actual value, your predicted value minus the y bar. Again, why are we comparing, guys, the predicted value and your y hat, y bar, your average? It's because the initial base base value that we have for predicting y is just your average. And then by coming up with the regression line, okay, our predicted value will now be based on the regression line and not just the average. So if we compare the average y bar and the regression, the forecast value, that is how our model improved. Okay, imagine, guys, take a look again at our illustration. If we just use this line, the y bar, as our base forecast, then there will be a lot of figures of points that are very far from your y average. Now compare that with this regression line, this dotted line here, and you notice that some of the points are now exactly on the line. And the deviation, the distance between the actual points and your regression line is closer compared to just using the base forecast, which is your y bar. In other words, guys, there was an improvement in our model, because now we're able to compute for your predicted value y hat or forecasted value y hat, okay, and there's an improvement as compared to the y bar. So for SSR, for some of the squares of your regression, we're going to compare the predicted value. This is the predicted value y hat. This is our average value. The difference between them is our improvement. And then we have to square that, because if we don't square that, guys, and then if we sum it, then we'll just get 0. All right, so let's do that. Okay, our y hat is the predicted value. This is our y hat, the predicted value. Let me put this in parentheses. And then we subtract the base estimate, which is just your average. Okay, average of y. And then once again, I'm going to fix the row. All right, so this formula is our predicted value of y, this one, minus the y bar. Okay, I hope it's clear to you guys that in this, here in SSR, sum of the squares of the regression, we're comparing our first model, which is just the average, our base model, which is just the average, and the regression. And we'd like to see the improvement of the model. So we're getting the difference between the mean and the predicted value, and then squaring it. So we have to square this also. Otherwise, if we don't square it, the sum will just be equal to 0. Okay. Now take a look at this, guys. Okay, so initially, the total, sum of the squares of the total, which means a deviation from the actual data point to the mean, okay, which is the base estimate that we have, it was this 3.26, 3.27 trillion. Now with the regression, guys, what happened was 1, 2, 3, 4. So million, this is million, billion. Oops, is this correct? 1, 2, 3, 4, 5. 2, 3, 4, 5. Wait, did I make a mistake here? Y hat minus, yeah, that's correct. Y bar. Y hat minus Y bar. Y hat minus Y bar squared. Two, 3, 4, 5. Okay. There's, I think I have a mistake here. Y sub I. Let me check this. Y sub I. Y sub I. Sorry. My apologies, guys. This should be Y sub yes, actual minus Y bar. This is correct. Sorry. Okay, let me just pause for a while. Okay, I saw the mistake. Okay, so I did an error on the predicted value. The predicted value should be the slope times your x plus the intercept. So I made the mistake here. Okay, B201. Okay, this is wrong. It should be the intercept. Okay, this one. Oops, sorry. Okay, sorry. Let me redo this. So this is equal to. So we first have the intercept. This is the intercept. And then we fix this. And then plus x sub I. This is our actual. Okay. Plus the slope. Where is the slope? This is the slope. Let me fix that. Times the actual value of x. There. Okay. Apologies, guys. Okay, so this is your predicted. Okay. All right. So now we're now correct. Okay, so going back here, guys, y hat, this is our predicted value, minus y bar. So I'm now subtracting the predicted value minus the average and then squaring it. Okay, and then add the deviation squared. you get SSR, sum of the squares of your regression. Okay, so 2.75. This was the total, let's say the total deviation. Was a total deviation squared, or actually your variance. Okay, of this 3.26, we were able to explain 2.75 because we improved from the mean to the regression line. Okay, this was the improvement. Okay, and then lastly, guys, last is this was our model, but not everything was captured by our linear model. Okay, what do I mean by not everything was captured by our linear model? If you can see, guys, in our model, not all the points are on the regression line. So there are many points there that are outside the regression line. Okay, so for example, for this point, okay, our predicted value was this one, but the actual was this one. So that means that there was an error here by this amount. When I say error, it missed. When you compare the actual from the model, regression model, you were not able to capture the the actual value of y. Okay, so in this case, just a relatively smaller deviation. Okay, so there are some points that are exactly on the line, these points. But some points are quite far off. For example, for this one. Okay, now what we do, guys, is to compute for the difference. So this is your y sub I, the actual, minus, what's this, guys? What's this height? This is your predicted value. Okay, so we get the difference between your actual and your predicted. That's actually your residual. That's actually your error term, right? Kasi we were not able to predict correctly the value of your sales. Okay, so that deviation is if we square those deviations, okay, and then add it, you'll get what we call SSE, sum of the squares of your error terms. So how do we compute this? We need to get the difference between your actual data point and your predicted value. Your predicted value lines all lies in this regression line. Okay, so let's do that. So the predicted value is just the difference between your actual data point minus the predicted value. Now we already have your actual data point. This is your actual, your sales, minus the predicted, this one. Okay, so this is the difference between your actual and your predicted. So we can now square this deviation. So we just use this. This is your error terms, and then square it. Let me just... sorry. Need to... All right, so this is error squared. Okay, let me remove the... No need for us to put in the decimal places. Okay, error squared. So that's a difference between your actual data point and your predicted value. Okay. And then add it also. There. All right, so this is your SST, this is your SSR, this is your SSE. Sum of the squares of the total. This is the deviation of your Y value from the average, okay? Squared deviation, the total. And then this is the deviation between your mean from the predicted value from your regression line. Again, get the difference, get the deviation, square it, and then add the total. And then this is now the deviation between your actual data points and your forecasted line. Okay, so of the total variation of 3.26 trillion SST, we were able to explain using the regression 2.75 trillion. Okay? That which we were not able to explain is in SSE. That's 516 billion. Okay, so let's continue working on our problem here. Okay, SST. So what's SST? This is the sum of the squares of your total, and let's just link it here. This one, so that's your SST. Okay, then your SSR, this is our SSR, sum of the squares of our regression. And this is the sum of the squares of our error terms or our residuals. This one. Okay, now take note, there's an important relationship between SST, SSR, and SSE. What do you think is the relationship between SSR, SST, and SSE? So we have here SST. SST is equal to the sum of your SSR plus SSE. Okay? So that means, guys, that the total variability of your dependent variable, which is your sales, can be broken down into components. SSR, okay, that is the variability that can be explained by your regression model, and SSE, the variability that cannot be explained by your regression model. So let's see if this adds up. So this is equal to this plus this. There. Okay, so this confirms the fact that your SST, sum of the squares of your total, is the same as the sum of your SSR and SSE. Now that's very, very important because we're going to use that to expound more on regression. Okay, so let's continue solving this. Now, okay, if this is the total variation of your dependent variable, and this is the total variation that was explained by your regression model, we can get the ratio of that. So let me write here. So we know that SST, sorry, is equal to SSR plus SSE. If I divide everything by SST, and your SST. Okay? All right, SST over SST, this is 1 or this is 100%. And then this is SSR over SST. This is the variation, okay, that can be captured by our regression line, that can be captured by our model. And this is the variation that cannot be captured by the model. Okay, so this is your unexplained variance. This is your explained variance, as explained by the regression line. Okay, so that's very important, guys. SST is equal to SSR plus SSE. And again, if we divide everything by SST, we come up with this proportion, 100% is equal to this, what we call this explained variance. Explained because we were able to capture the variability of your dependent variable using the regression line. Okay, so let's just have some, let's continue with the computation. All right, so we're asked to compute for SSR over SST. Our SSR is this one divided by SST, which is this one. Okay, take a look at this. Does this look familiar? 0.8412. Yes, guys, that's we have already discussed that. That's actually your coefficient of determination. And remember, guys, your coefficient of determination tells us, okay, that tells us the variability of your dependent variable that can be explained by your independent variable. So your dependent variable, sales, 84% of its variability can be explained by your ads. 84.2% can be explained by your ads. Okay? Clear, guys? Clear? All right. So that's one way to compute for your R squared. Okay. Another way, guys, is what's another way to compute for our R squared? Remember, R squared is related to your correlation, right? This is correlation. Uh, Another formula is actually R. So let's use RSQ. Okay, so what's RSQ? Returns the square of the Pearson product moment correlation. So it's actually R squared, okay? R squared. Okay, R squared, known y's and known x's. So we can compute for your coefficient of determination, known y's, comma, known x's. All right, so it's the same, guys. It's the same. Or another way to compute for your coefficient of determination R squared is, if we take a look at this, so this is your R squared actually, right? Plus SSE over SST. Okay, so your R squared, which is SSR over SST, can be computed using this. R squared is equal to 100% is just 1 minus SSE over SST. Okay, so this is 100% of the variability of the variance. Then this is the unexplained variance. Okay, so the total variance minus the unexplained variance is your explained variance, right? So, and that's represented by your R squared. So let's do that. Okay, so it's equal to 1 minus SSE, okay, the unexplained variance over SST. And then you get the same 0.84, exactly the same. Okay? All right. Then there's another one here. Okay, we can compute it using the correlation. Remember this, guys? It's equal to correlation. Correlation, so that's RA1 and RA2. So that's the correlation, guy. Oops, sorry. Why did I write it here? Okay, so we use the correlation, guys. Correlation, then, but we have to square that. No? And then square it, because our coefficient of determination is correlation squared. There. Okay, the same. All right, so I go here. Okay, so what does that mean, guys? What does this mean? 84.2%, which is your R, which is your, sorry, this is your R squared, okay? R squared, it means total, this is 84.2%. This is your SSR. And it means that the total, the total variability, 84.2% of that can be explained by your regression line. So if we use the regression line, then we can explain the variation, the variability of your dependent variable sales. Or 84.2% of the variation in Y in your sales can be explained by your regression line. Or 84.2% indicates a strong fit of the regression line to the XY sample data points. Okay, so we have here several explanations, okay, for our coefficient of determination. All right? Okay. Okay, so let's just compute for this, and then I'll explain this in the next section. Okay, first, how many independent variables do we have? We have only one. We have only one independent variable, and that's your weekly ads. We can, of course, use several independent variables, and that will be the case of a multiple linear regression. Okay, now, the degree of freedom, okay, n minus q minus 1. So that's, what's our n? N is 190, okay. N minus q is your number of independent variables, minus 1, minus 1. That's for the degree of freedom for reduction in the degree of freedom because we have to estimate the intercept. Okay, now take a look at this, MSE. MSE. One measure that's very important to us of the unexplained variance. Okay, because we'd like to have, of course, we'd like to have a very high R squared. Because a high R squared means that a high percent of the variability of our dependent variable can be explained by our regression model. Okay, so first we compute for the mean square error. The mean is average. Square error, that's your SSE. We have our SSE here. Okay, our SSE is this amount. And then we're going to divide it by its mean. So we're going to divide it by your degree of freedom. So this is the degree of freedom for your residuals, for your error terms. So that's this one, okay? So this is our mean square error. And then we will have to compute for the standard deviation of the estimate. That's a standard deviation of our error terms. So how do we compute for this? How do we compute for this? We just have to get the square root of this. Okay? This is sum of the squares of the error. This is actually your variance of the unexplained variance. And then if you get the square root of the unexplained variance, then we're able to get the standard deviation of the unexplained variance. So that's also the standard error of our estimate. So it's equal to SQRT, this one. All right, so this is our standard error of the estimate. Okay, there's another way to compute for this, and it's equal to stakes. Okay, here, stakes returns standard error of the predicted Y value for each X in a regression. So let's use stakes, known Y's, known X's, known Y's, comma, known X's. Okay, they're the same. Okay. All right. Now I leave this first, guys. Okay, I showed you the measure for the standard error of the estimate, or SEE. That's actually the standard error. It suggests that on the average, our estimate will deviate from the by an average of 52,000. So we will be off. Our estimate using our regression line will be off by around $52,423. Okay. So as I said a while ago, the higher the R squared, the better. Okay. A high R squared means a lower SSE over SST, right? And based on SSE, we will compute for the standard error of the estimate. Okay. So the standard error of the estimate tells us how fairly our regression line represents our data points. Okay, so here our standard error of the estimate is around 52,000. It means that on the average, we will be off. Our actual will be off from the regression line by 52,000. The lower this SEE is, the better. A lower standard error of the estimate, of course, the better the model is. Okay, so let me just end in this first. I hope you follow this, follow along, and should you have any questions, please feel free to PM me. Within the week, also I'm going to send another video. This time, we're going to do the regression, and I'm going to explain using real stats the regression model uh, for for these data points. Okay, so let me end here.